to ASMR Chemistry. This is a classroom space where I take my many years of teaching as a college professor and I use calligraphy pens or chalkboard or maybe iPads in the future to teach many of the concepts that some of you struggle with, or maybe you just want to review while you relax. So what I wanted to do today is look at some organic molecules shown with line angle drawings and then practice identifying what is the hybridization on each of the atoms within these molecules. Okay, so we will just do a smattering of different kinds of molecules, different functional groups on them, and see what the hybridization is. Okay, so let's start with this molecule here. Okay, so as we can see here with line angle drawings, we have our carbons, those 4 carbons. Okay. Oftentimes in line angle drawings with functional groups, we don't see the lone pairs. So one of our jobs is to identify where there are lone pairs. So this nitrogen, because it's bonded to carbon there with a single bond, and it's got these 2 hydrogens, it will have a lone pair. And this oxygen will also have lone pairs. So that can help us identify the hybridization of each of these atoms. So I'm going to get a different colored chalk to do that. Let's see, I'll use pink. Okay, so let's start with this carbon here. It has these 3 implied hydrogens. It's all single bonds. So we would expect this to be sp3, that carbon there. And the same will be true for this carbon. Any of these carbons that have 4 bonds, single bonds, we expect to be sp3. Okay, but what about this one? Okay, so now we have a carbon. There's 2 sigma bonds, single sigma bonds. And then here's a double bond. 1 sigma, 1's pi. And if there's a pi bond, it means that we need to have a pure unhybridized p orbital in order to overlap with that of the oxygen and create the pi bond for this double bond here. So that means this carbon is sp2, this one right there. Okay, so same is true for this oxygen. It is sp2. The sp2 hybridized orbitals are used for sigma bonds and to hold lone pairs. So we have 3 of those hybridized orbitals, which are sp2, and then there's one leftover unhybridized p orbital that creates that double bond to the carbon. Okay, this carbon here, just like this one, sp3, and this nitrogen has single bond to the carbon, single bond to one of these hydrogens, single bond to the other hydrogen, and a lone pair. So here, this needs 4 hybrid orbitals for the single bonds and the lone pair. So this nitrogen is sp3. Okay. All right, let's look at another example of a molecule. Oh, and by the way, if we're reviewing functional groups, this is a ketone, and this is an amine group. Okay. Let's look at another one. Okay. I'm like thinking a little too hard here. Pause for a second. Okay. And I wanted to have all right, functional groups here. Here we have an alkyne. It's a triple bond. And over here we've got a C double bond O next to an OH group. So collectively, this is a carboxylic acid. By virtue of having this oxygen here alongside this oxygen, it weakens the bond between the oxygen and the hydrogen, making this hydrogen acidic, meaning that this oxygen-hydrogen bond is weaker than usual, and this is a carboxylic acid. Okay, so in terms of looking at the hybridization of these, okay, some of this will look similar to what we just did. Let's start out just reminding ourselves where we would expect to have lone pairs. Sometimes that can help identify what the hybridization would be. Okay, so here we've got oxygen, the single bond here, single bond there, 2 lone pairs. So this would be sp3 hybridized. Meanwhile, this carbon and this oxygen is exactly what we saw up here, right? Carbon, oxygen. We decided those were sp2. sp2, where we've got 3 sigma bonds and 1 pi bond. sp2 for that carbon, and sp2 for this oxygen. This carbon here, single bonds to the 2 carbons around it and the 2 hydrogens that are implied but not shown. So there's sp3, and same with this one, sp3. Okay. Now, what about this carbon and this carbon? Okay. Now we've got not only a sigma bond here, but 2 pi bonds. And for each pi bond, the carbon here and here, they need to have 2 pure, unhybridized p orbitals in order to overlap with the other carbon and create this triple bond. So that means that each one of these, let's see, I'll put it here, each one of these carbons is sp hybridized. This one and this one. And I wanted wanted to show you also that you don't always have to have a triple bond to see sp hybridization. And a very iconic example of that is CO2. So let's start here. Carbon dioxide. Getting really close to this, so I'm going to draw a little line. Separate this two. Okay. So let's put in our lone pairs. Okay. So let's take a look at this carbon. This carbon has a single bond. I'm sorry, not single bond, but a sigma bond. Sigma bond. I'm just labeling these. Sigma. Sigma means that the electron density is directly between the two nuclei. Okay? And sigma bonds are created with hybridized orbitals. So this carbon has two hybrid orbitals that are 180 degrees from each other. And this carbon also has a pi bond going to this oxygen and pi bond going to this oxygen. So it needs to have two pure unhybridized p orbitals in order to create the pi bond going in this direction and in this direction. So here's an example of an atom that is sp hybridized, but it does not have a triple bond. But you'll see it does have two pi bonds to it. Just like over here, this carbon has two pi bonds. They happen to both be going to the same other atom. In this case, the two pi bonds are going two different directions. Okay, so that's why it's helpful to look at the number of sigma bonds you have. Those are used for the hybridized orbitals, used for sigma bonds and to hold the lone pairs. The pi bonds are the unhybridized p orbitals. Okay. Let's do one more thing, and that is look at these molecules and write down what are the bond angles. Okay, so put these down and let's choose another color. Go with green. Okay, this one we acknowledged was 180. That is consistent with sp hybrid orbitals. They're 180 degrees from each other. So that's also true here. 180 degrees around this sp hybridized carbon right there. sp3. Not a lot of room here, right, to draw sp3, so why don't we look at this one where there's a little bit more room. sp3 hybridization corresponds to 109.5 degrees. And sp2 bond angles are 120. Get that in there. Okay. If we wanted to also look at the naming the geometry around each one of these. We can do that as well. So for example, with this sp3 hybridized carbon, where it is bonded to 4 other things, carbons and hydrogens, this would be tetrahedral. This nitrogen here, because there's a lone pair, we would call the geometry around this nitrogen trigonal pyramid. The geometry around this sp2 hybridized carbon right here, with the 120 degrees around it, this is trigonal planar, because this carbon here has these 3 atoms around it, and they're all in a plane with 120 degrees. Okay. Well, I hope that was helpful for you. I'm really enjoying doing these with the chalk, but I will go back to the calligraphy, I'm sure, and I just got a skin for my iPad that I think might be really nice for drawing, so I'm going to be trying that out soon. So watch for that. As always, keep your requests coming. I love helping you with the things that you need help with, and I'm always happy to do that. So take care, and I want you all to do well at chemistry, and I am here to help. All right, I will see you next time.